The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let me start here with the temperature dependence of K. And this turns out to be extremely important, and it's due to Arrhenius in 1889. And Mr. Arrhenius is famous for many reasons, not just for his rate law, but as I learned recently, it turns out that he was also one of the first people to calculate the potential effect of carbon dioxide in the atmosphere and its potential effect on global warming. This was the Industrial Revolution, and people were starting to use fossil fuels at increasing amounts. And back then already, some people started to get worried. And so he did the calculation. It was a very crude calculation. And he extrapolated, assuming that the rate of fossil fuel use would keep going. He got his calculation pretty much right. What he didn't get right was the amount of fossil fuel that people would be using. And so when he did his calculation, which is, again, a very crude calculation, he got that we would get in trouble at about 2,000 years from the time of his calculation. So he said, no problem. 2,000 years, we've got a lot of time. And ever since then, people have redone these calculations and more and more sophisticated. But his crude calculation was good enough. And as people redo the calculations, the time that they say we're in trouble to the time of the calculation gets closer and closer together. And the reason for that isn't that their calculations are wrong. It's that the rate at which we put out carbon dioxide just keeps getting faster and faster and faster. So it's interesting to go back to these calculations through the last century and a half and see that. Anyway, so Mr. Arrhenius predicted global warming. And he wrote his rate equation, K is equal to e to the minus EA over RT, famous Arrhenius rate equation. If you plot it as log of K is equal to log A minus EA over RT, you find that it looks like a straight line with an intercept at log A, where A is the prefactor here, and EA is going to be the activation energy. And the slope is EA minus EA over RT. R is the gas constant. T is the temperature. And if you put in some typical numbers, activation energies typically are on the order of a few tens to hundreds of kilojoules per mole. Let's say 50 to 300 kilojoules per mole. And typical activation factors, typical pre-exponential factors are, depending if it's a first order or second order, let's say first order, 10 to the 12th, 10 to the 15th per second. So the A carries the units for the rate here. So if you have a, so this is for first order. If you have a second order, then the units of A will be different. And typically, they're going to be on the order of 10 to the 11th or so, 10 to the 10th, 10 to the 12th, 1 over a molar per second for second order. And it's interesting to do sort of a back of the envelope example to figure out how important this rate is. And one of the interesting things to look at is, suppose that I'm at some temperature and I want to know, how do I change the temperature? How much do I need to change the temperature to double the rate? Okay? And let's say my temperature let's say T1 is on the order of 300 degrees Kelvin, room temperature. Room temperature, and let's take a typical EA on the order of 100 kilojoules per mole. The room temperature or body temperature are roughly the same, right, as things are. And so the question is, what does T2 need to be to double a rate connected with an activation energy, which is fairly typical of 100 kilojoules per mole? So we want to know what is, if I have K2 over K1 is equal to 2, what's the new T2? So A e to the minus EA over R T2 divided by A e to the minus EA over R T1. We want that equal to 2. The A's cancel out. So log K2 over K1, which is equal to log 2, is equal to EA over R, 1 over T1 minus 1 over T2. We know what this is. We know what this is. We solve for T2, and you find that T2 is 305 degrees Kelvin. It's a pretty small change to double the rate. So it's pretty important that your body temperature doesn't change very much. If you have a fever and your temperature goes up and the rates start going up in your body, right? You could cause a lot of problems if the rates of some reactions go up by a factor of 2. So it's very sensitive to temperature. Rates are very sensitive to temperature. What are these things physically, EA and the pre-exponential factor? Let's take a look at that. So physically what's going on is you have your two, let's say it's a bimolecular reaction, A plus B goes to C. So mechanistically what we think is happening is that the molecules come together and collide, right? You have A and B getting together and colliding. And the hypothesis is that when they collide, they form a complex. They sort of bind together momentarily and form this complex that has all the kinetic energy, or part of the kinetic energy of this collision as part of it. So A and B are bound together in some highly excited complex, which then falls apart to give the product by rearranging its atoms around. And if you plot the energy of this process, as a function of the reaction, we call this the reaction coordinate. Then we're going to start at some delta G or some energy for the reactants. We're going to end up with some energy for the products, and it could be higher or lower. Let me make them higher here, just because I don't have enough room on the board. Products. So this is an endothermic reaction. That's the energy for C. This is the energy for A plus B. And then along the way, we have this complex that captures some of the energy of the collision up here somewhere. Okay, and this is the energy then of A, B star, which we call the activated complex. So for the reaction to happen, then we have to go over the barrier and then back to the product. And this distance from the energy of the reactants to the top of the barrier, that's EA. That's the energy of activation. How much extra energy you have to put in there to go over the barrier. So it's very clear that as you increase the temperature and you increase the amount of energy that the reactants thermally have, or in terms of their kinetic energy, as you raise the temperature, you get more and more kinetic energy. You're going up higher and higher in the Boltzmann distribution. And the number of reactants that can make it over the barrier clearly goes up exponentially as the temperature goes up. So this is EA for the forward reaction. Clearly, there's going to be an equivalent activation energy for the backward reaction, and the two are related. The difference between the forward and the backward reaction, so E backwards minus EA forward, gives you the delta G for the reaction itself. Right, so EA backwards minus EA forwards gives you delta E for the reaction, where E could be enthalpy or could be free energy. So that's the physical origin of this EA, this activation energy. Now A, the pre-exponential factor, that's called that's the rate of attempt for the molecules to try to go over the barrier, right? So it has units that make sense for that. Okay, and this A is different than this molecule here, rate of attempt. How many times per unit time, or how many times per second, do these two molecules try to collide? Right? If they never collide, if they never try, they'll never make it over. So it's any for a 1/2 or 1 mole second. So if this is the rate of attempt, then E to the minus EA over RT is the probability of success of making it over the barrier. Right? So the rate of attempt times the probability of success gives you the rate per unit time of making it over the barrier. Okay, any questions on the dissection of this Arrhenius rate law? All right, so here's some examples, a few examples that you know of. Let's look at OH minus plus methyl bromide. Displacement reaction going to this OH minus attacks the carbon right here to form an activated complex, H, 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 with the OH coming in like this. Whoops, let me go like this. Okay, there's the intermediate right here, the activated complex in your reaction, which then falls apart. It can fall apart two ways. The OH can be spit out again, forming back to the reactants, or the bromine can be spit out, forming the product, which in this case here is methanol. H, 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 OH, plus Br minus. Typical example. So given this picture here, which you're probably already somewhat familiar with, we can then move on to talk about how to affect this barrier, how to change the rate. Oh, I should say a couple more things, one more thing too. Now the rate of, so clearly the EAs are related, right? Because the difference of the two EAs is the delta E for the reaction. But the pre-exponential factors, these A's, for the forward reaction and the backward reactions aren't necessarily related. You can imagine that in one case you have, first of all, they don't even have to have the same units. Right? You could have a bimolecular reaction one way and a unimolecular reaction the other way. Right? So you can't really say anything about the forward versus the backward rate this way. All you know is about the energies. Okay, catalysis. So now we have this barrier we have to overcome. And so suppose that you have, to motivate it, suppose you have an equilibrium case which is slow, and a reaction which is slow in both directions, K1, K minus 1. And you don't want to wait for this to happen. And this could be in a biological environment, or it could be an industrial process, like the Haber process. You don't want to wait. And so one of the ways that you can speed it up, is by changing the temperature. Right? You change the temperature, the rate goes up. You change it by 5 degrees, the rate goes up by a factor of 2. You can make a huge change by changing the temperature. But, so if you raise T, speeds up. But the equilibrium also changes. And we saw that when we did the Haber process, right? We raised the temperature, the rate speeds up, but the equilibrium switches to the reactants. That's no good. So changing the temperature is not always the best thing to do if you want to change the rate. Instead, what you can do is use a catalyst, if you find one. A molecule that reacts with your reactant to form a product, in this case B, spitting back that molecule C again without using it up. And now with the activation energy, we can understand what the catalyst does. What the catalyst does is it speeds up those rates K2 and K minus 2 by changing the activation energy by making it be smaller. So now I have a catalyst, and I can make this energy smaller. So this would be A plus AC activated, getting ready to spit out B. So in my example here where I have A plus B goes to products, so I would have some combination of A, B, and C together to give out the products. Okay, in this case here, the difference in energies doesn't change. All that you're changing is the hump in both ways. Equilibrium constant doesn't change, just the rate changes through the Arrhenius rate law. And this is extremely powerful, especially in biology. So let me give you some examples here. This is sort of a typical example of increase in rates. Let's say you have the reaction hydrogen peroxide goes to water plus oxygen. If you take a little bit of hydrogen peroxide and you put it on your skin, it starts to bubble, right? But if you let it sit on the bottle, nothing happens to it. Right? Put it on your hair turns white or blonde. But again, if you just let it sit in the bottle, very little happens. Or it happens, but very, very slowly over time. So if you look at the rate of this reaction here, if that's the rate moles per second, with no catalyst at all, the rate is 10 to the minus 8 molar per second, which is very slow. And the activation energy in kilojoules per mole, in this case here is 71 kilojoules per mole. Now we can start adding catalysts. We can start adding an inorganic catalyst like hydrogen bromide, increase the rate to 10 to the minus 4. So this creates a complex with the hydrogen peroxide, which lowers the barrier to 50 kilojoules per mole, a small amount of lowering, but because the energy is in the exponent there, it makes a big change in the rate. Yes?
So with that catalyst HBr, are you assuming that the catalyst, that the rate is independent of the catalyst concentration?
the rate is independent of the catalyst concentration. The rate would have to change. You're right. That's a good question, and I'm not prepared to answer it. Okay, I'm going to have to think about this. Okay. Let's pretend now that we're at per unit concentration of the catalyst, okay? And then I'll look into it. All right, so this is what happens with an inorganic catalyst. And instead, if you use a generic biological catalyst, an enzyme catalase, it's a sort of ubiquitous enzyme, which is why you have it on your skin, et cetera, then this rate becomes 10 to the 7th. And the activation energy drops to drops to 8 kilojoules per mole. So your question really has to do with the units of A, of the prefactor right here. Yeah. Okay, and so there are all these examples of reactions that are very important biologically, where with an inorganic catalyst or an organic catalyst, you can change the rate by maybe a few orders of magnitude. But as soon as you put in an enzyme, the rate changes by 10 orders of magnitude, or in this case, 8 plus 7, 15 orders of magnitude. Right? Humongous change in the rate. So you've probably done some enzyme catalysis before, but it's probably a good idea to quickly do it again. Because it's just so important. And it ties together our approximations that we've learned about. So enzyme catalysis, so enzymes can be either, can be heterogeneous catalysis, can be homogeneous catalysis. Enzymes are ubiquitous in the biological environment. They serve to regulate the cellular activity in very complicated ways. The cell will upregulate or downregulate enzymes, the concentration of enzymes as it needs to make or more or less products. And there's whole cascades of events that happen in this way. And they're in very small concentrations, but they play an extremely important role because they're also extremely specific. So you can have an enzyme that will only act on one part of the biological cycle and affected by 10 orders of magnitude or 15 orders of magnitude, but not affect any other protein that's around. And that's amazing. And it turns out that a lot of the diseases of old age, like what I'm about to face or I'm facing already, not yet, but are the result of some of these enzyme upregulation and downregulation beginning to break down. So we have all these reactions going on that need to be essentially perfect, right? When you have DNA replication or protein folding or things like this. And errors are made. Errors are made all the time in these processes. And errors cause diseases. And so even as a baby, your biological processes make errors. But you have these processes, these enzymes, especially based on enzymes, that can go in there and sort of fix things, right? Fix things and make sure that you don't end up getting Alzheimer's at age 6 months. Right? But as we get older, for some reason, these processes, these repair processes, they lose their bearings, just like we lose our bearings. And they can't repair things anymore. Don't do it very well. And that causes all sorts of diseases. Cancer is probably one of the diseases due to the lack of being able to repair problems. Alzheimer's, all sorts of dementias, MS. You just name a chronic disease, and it's probably due to a problem with upregulation or downregulation of some proteins and some enzymes that are due to a repair process. So anyway, these enzymes are big proteins. Ten to the fourth, 10 to the sixth molecular weight proteins, on that order or so. They tend to be fairly large in size, on the order of nanometers. Let's say 10 nanometers to 100 nanometers. That's a little bit on the big side, probably closer to 10 nanometers. 100 nanometers is kind of big for any sort of biological molecule. And they always end with their name A's, like catalase, urease, RNase, esterase, clips ester bonds. Your liver is full of esterases because it likes to break things down into smaller and smaller pieces, and lots of ester bonds and things that are not very biologically interesting, and that's one way of the liver breaking things down. Okay, so the way it works is that you have your reactants, which in the biological language are called your substrate. Come into an enzyme, gets bound up in the pocket of, there's the substrate, the reactant, there's the enzyme here, forms a complex, and then product gets spit out. And the product floats off and does its thing. It probably gets bound to another enzyme, which makes another product, et cetera, and the cascade goes on. The signaling cascade goes on. And this enzyme is in very small concentration. The product goes away, so that's going to stay as a very small concentration as well. All right, so what's observed experimentally then? Experimentally, what's seen is that the substrate makes products in the presence of the enzyme with a rate, dp dt, that's at t equals 0, this is the initial rate, is proportional to the concentration of the enzyme, this initial rate. And in the language of enzymatic kinetics, this is called the velocity. dp dt is also called the velocity. Velocity, moles per unit time. And this would be called then the initial velocity of V initial. V initial is proportional to the enzyme concentration. What else is seen? For fixed, if I fix my concentration of enzyme and I look at the velocity over time, let's say minus ds dt, which is dp dt, I find that that's proportional to S for small s, for small concentration of substrate. And then at large concentration, it's a constant. So it's not a straight line. In fact, I don't want to do it on this board. I'll do it on this board here. Plot the concentration of substrate on this axis, and I plot the velocity or the rate of the reaction on that axis here. What I find is that it's a constant, so it's going to saturate. The rate is going to saturate to some number. and it's going to start linear with substrate at the beginning. So it's going to be a straight line at the beginning. And eventually, it will saturate. That's that sort of slope here. And the saturation point, that's the maximum velocity, or the maximum rate that it can have. So we call this V max. In this part here, the velocity is proportional to S. And somehow we have to explain this using what we know from kinetics. So we have to come up with a mechanism and then solve the mechanism, right, and make sure that it reproduces the data. All right, so we're not the first ones to do this, obviously. Michaelis and Manton did this many years ago for this mechanism. And the idea is you have the enzyme plus the substrate react K1, K minus 1 to form a complex, enzyme substrate complex. But unlike what we've drawn before in terms of this hump, where there's an activated complex which is not stable, in this case here, this enzyme substrate combination lasts a long enough time that it's basically a stable complex. Okay, so we're going to write this as a real intermediate that lasts long enough for you to be able to fish it out and characterize it. And then eventually that K2, K minus 2 goes to product plus enzyme. So the enzyme is a catalyst that forms a long-lived complex. And if you were to draw this then in our energy diagram, where we have the reaction coordinate here, you start out with your enzyme plus substrate. You go up, and you form your intermediate up here, ES. And I put a little dimple in there because it's stable enough that it's not on the top of the hump, but it lives long enough. And it comes back down to form the product plus the enzyme. Okay? Without the enzyme in there, this hump would be way, way up there. It would be maybe a factor of 10 higher. So this really lowers it a lot. OK, now we can start to solve this mechanism. And I forgot one arrow here, which is the arrow going back, which you usually don't see, but we might as well keep it there for the sake of completeness. OK, so what do we know? We know that this intermediate concentration is very small. The enzyme concentration itself is very small. The intermediate is very small, and it doesn't change very much. Not changing much. Okay. And so that means that we need to use a steady state approximation. So let's write down the rate for this intermediate, ds dt. It gets formed through the forward process. I'm going to put my brackets back in because E and ES would look the same otherwise. Gets destroyed through the backward ways, and I'm going to use a steady state approximation. So I'm already going to start adding steady state here every time I see an intermediate. Get it destroyed to make products. It gets recreated through the backwards reaction from the products. And I'm going to set that equal to 0 for the steady state approximation. Okay. Now, we don't really want to have this E floating around here because this is something that is very hard to measure. It's much easier to measure the initial concentration of the enzyme, right? What you put in there instead of the amount that's not being bound up. So we're going to solve instead in terms of E is equal to E naught minus ES, where this is the initial concentration and this is the amount that's that's binding substrate, and this is the amount of free enzyme here then. And when you do that, and you plug in here, and you plug in here, you get your result, which is that E steady state, ES steady state, is this ratio K1 times S plus K minus 2 times the product divided by K minus 1 plus K2 plus K1 times S plus K minus 2 times the product times proportional to the initial concentration of enzyme. Okay, and then you can take your steady state approximation for the intermediate and plug it back into your rate equation. So the velocity we defined, that's the rate, which is minus ds dt, which is K1 times E times S. This is the destruction of the substrate minus K minus 1 times the S steady state. There, backwards process. So we put in terms of this E, we put in E is equal to E naught minus E S steady state. And then we put in for ES steady state, we put in what we found here. We turn the crank on the algebra, and we find that the velocity then is K1, K2 times the substrate concentration minus K minus 1 times K minus 2 times the product concentration, the whole thing times the initial enzyme concentration, and then K minus 1 plus K2 on the bottom plus K1 S plus K minus 2 times the product. Okay, so as I mentioned, this product here usually just floats away. And so at the locally where you're doing and it gets used up. It gets used up by the next step in the cycle. So this is pretty much zero. You can pretty much ignore this. You can ignore this guy here too, because it's not, you don't have a steady state or an equilibrium. You have a steady state, but not an equilibrium situation. And so in that case here, you can rewrite this then as K1 K2 times the substrate times E naught divided by K minus 1 plus K2 plus K1 times the substrate. And now we can look at these experimental observations and see whether they match our mechanism, if we can understand something. Okay, I can erase this guy here. So let's look at the initial rate. Initial rate is supposed to be proportional to the substrate, right? Initial rate is supposed to be proportional to the substrate. So the initial rate K1, K2 plus K1. Look at early times. Next one. So the initial rate is going to be somehow I've got the product missing here. no, I got it backwards here. This is not the initial rate. This is the rate where S is small. The initial rate is when you don't have any products made, or when the product concentration is very low. And because we're making the assumption that the product concentration is basically equal to 0 here, this is basically the initial rate here. So by taking the product equal to 0 here, we're also saying that this is the same thing as the initial rate. So this is what it looks like here, the initial rate here. And this is, this you rewrite as the initial is equal to K2 times S times E naught. You divide by K1 up and down, and you have this K minus 1 plus K2 over K1, and then plus S sitting down there. And you define this ratio of rates, K minus 1 plus K2 over K1, as the Km, the Michaelis constant by definition. And this is an interesting ratio. This is the rate, K minus 1 is the rate of destroying the enzyme substrate complex by going back to the reactants. K2 is the destruction of the complex by going to the product. And K1 is the creation of the complex. So this is the rate of destruction of the complex divided by the rate of creation of the complex. Right? So if the rate of destruction of the complex is much faster than the rate of creation, meaning that this is a large number, then you're not going to pile up any complex. It's going to be destroyed as soon as you create it. Right? So if Km is large, then the concentration, Es, is going to be very small, right, compared to E naught. But if the rate of destruction of the complex is small compared to the rate of creation, you create complexes, but you don't keep up in terms of destroying them, in terms of making products or going back to reactants. And so you end up saturating your enzyme. Every enzyme ends up having substrate bound to it. So when Km is very small, then Es goes to saturation. Okay? Basically, when Km is very small, then you're limited by the rate, the second rate in the process, of the enzyme falling apart to form the product. You have to wait until that happens, because then the product just floats away, right? And that becomes your rate limiting step. Okay, another way that you also will see this written is as this then is equal to, we'll define K cat as equal to K2, K cat times the enzyme concentration times the substrate, E naught, divided by Km plus substrate concentration. Okay. All right, so let's look at a few limiting cases then. First limiting case is suppose that S is large. Okay, let's take S to be much larger than Km. Because you look at the denominator and you see it's these, is this ratio of rates versus this concentration that's important here. Right? So in one case, Km is going to dominate, and the other limiting case, the substrate is concentration is going to dominate. So let's say that the substrate concentration dominates, meaning K sub m is small, in which case we already saw if K sub m is small, then you reach saturation. And in the equation then, the velocity, Km is small, S is large, the S's cancel out, and the velocity is equal to K cat times the initial substrate concentration. Both of these are constant. The velocity is constant. When the rate is constant, it's that limit up here that's experimentally seen. Okay? And the rate is depending on the initial substrate concentration, because all initial enzyme concentration, all the enzymes have a substrate in there. The more enzymes you have to begin with, the more intermediates you're going to have, the faster you're going to make products. And then it's going to depend on the rate, k cat, which is just k2, which is the rate of formation of products. That becomes the rate limiting step here. Okay, the other special case is if substrate concentration is very small compared to Km. And in that case here, and the other thing that we're going to do is we're going to, because we now understand this as this maximum rate up there, we're going to call this Vmax. Okay, k cat times E naught, we're going to call it Vmax. And so when S is very small, V then is equal to Vmax, which is k cat times E naught. This is Vmax here now, so we can rewrite this as Vmax times the substrate divided by Km plus the substrate concentration. Another way of writing it, capital K. Vmax times the substrate concentration, and we have Km plus S, but S is very small, so we drop it. And this is then proportional to the substrate concentration. And that's small substrate concentration compared to Km. We're sitting right here where it's linear, where the rate is linear. And there's a third place on the graph which is interesting, which is when the substrate concentration is equal to Km. In that case there, you plug S equals to Km, and you end up with a velocity then is equal to Vmax divided by 2. Okay. So when Ks is equal to Km, you are halfway up. There's Vmax over 2, and there's Km sitting here. When S is equal to Km, you're at Vmax over 2. Okay, and so enzymes then are labeled by their Kms, because that becomes very important to know how strongly they bind the substrate. Sometimes you want the enzyme to bind it very strongly, sometimes you don't. You want it to be fleeting. Depends on the role that the enzyme plays. Now there's a way to plot this that extracts out these important numbers, k cat and Km. And that's the Lineweaver-Burk plot. Lineweaver-Burk plot. And I just looked up this morning to see if Mr. Lineweaver was still alive. And as far as I can tell, he's still alive. He was 97 in 2003. So as of 2007, he was still alive. He's getting up there. One of the most cited papers, as you have in the notes, is in JAX, was the paper that showed how to go from this curved line to a straight line by plotting 1 over V versus S instead of V versus S. Okay, so if you take your equation and massage it, 1 over V Km over Vmax times S plus 1 over Vmax. We haven't done anything except rewrite the equation in terms of 1 over V versus 1 over S. So it becomes linear in 1 over S. And there's 1 over V sitting here. And you get a straight line with an intercept here. That's 1 over Vmax. And if you keep going, extrapolate out, you get this point here to be minus 1 over Km. And the slope is Km over Vmax. And Vmax was equal to k cat times E naught, so you get k cat out of this. Okay. So it's turned out to be a very useful plot. It's very easy to plot a straight line, especially before computers, the age of computers. And the referees, there were 6 referees that got this paper and pretty much turned it down because they didn't think there was any new chemistry in it, which is true. There's no new chemistry. It's just a way of rewriting the plot. But it was very important, nevertheless. Okay, any questions on catalysis, enzymes, Arrhenius? All right, so next time we'll do oscillating reactions and recap the course.